Hello everyone and welcome back to Minic Analytics. In this video, we are going to be exploring regression algorithms, basically conducting a comparative analysis, and by that we are going to be selecting the best algorithm in predicting house prices. So before we get started, as usual, if you are new to this place, please consider subscribing to our YouTube channel. We are welcoming you to this wonderful community. Hit that notification bell so that you never miss any of our video updates. You can also leave any comments, query behind because we love hearing from you. And so, let's get started. Possibly by now you have tackled different analysis where you have required to use different types of algorithms. So for this case, we will be comparing different types of algorithms with a given data set to compare and see which type of algorithm will work best given the type of data that we are going to be handling. For this case, I will be dealing with the data from the housing market. And as we know, the housing market involves a complex interplay of different types of factors. And therefore, by choosing the right algorithm is quite important to make accurate predictions. And as we all know, that the effectiveness of these algorithms vary based on the nature of the data that you are handling, as well as the problem that you are trying to solve. So therefore, different types of algorithms are best suited in some cases than other types of algorithms. So in this case, we are going to analyze data using multiple regression models to understand their strengths as well as their weaknesses, and ultimately identify the algorithm that works best for our particular data set. Also in the analysis, we'll be using different types of evaluation metrics, and we are going to be ranking these algorithms based on those evaluation metrics. And some of those metrics include the mean squared error, the R squared, as well as other types of metrics. So these metrics will also serve as a guide or a compass to guide us on the appropriate algorithm that best captures the patterns in the housing data that we are going to be analyzing. So the types of algorithms that we are going to be analyzing include that we are going to be using include the linear regression. So for linear regression, we know this is a model. It models the relationship between the target variable as well as the predictors as a linear equation. The lasso regression, the ridge regression, and the elastic net regression, those are variants of the linear regression. Also, we'll be using the k-neighbors regressor. For this, as for the k-neighbors, it predicts the target variable based on the average of its k-neighbors. And for the support vectors, this is just an extension of the support vector machine. And when we are applying a support vector regressor, we're just aiming to fit a hyperplane that in most cases tries to minimize the prediction errors. Also, when we are going to be assessing our model, as I said, we are going to be using different types of evaluation metrics. And one of them will be the mean squared error. And this is when we use the mean squared error, we are just trying to calculate the average of the square difference between the predicted values. So the predicted values will come from our regression, from our machine learning algorithms, while the actual values will be the actual values from our data. Another metric will be the R squared, where it represents how the model fits the data. So it ranges from 0 to 1, and a higher R squared value indicates that a better fit of the model to the data. Another evaluation metric will be the mean absolute error, which is the average of the absolute difference between the predicted as well as the actual value, while the root mean squared will be the square root of the mean squared error. So again, those are the evaluation metrics that we will be using, and they'll be guiding us to be able to rank the best performing algorithm to the least performing algorithm. Okay, so by now I think you have a better understanding of what you are going to be doing. So I'm going to jump right into the analysis part. Okay, so let's start doing our analysis. So for our analysis, I'm going to be using Google Colabs. So this is another IDE, this is another environment that data analysis can use for the analysis. Okay, so for this analysis, we will start by importing the Python libraries. So as you can see, I have imported several types of libraries. So those include the pandas. So I've pandas, the NumPy, matplotlib, seaborn, as well as plotly. So I'm going to execute this cell to ensure that I have successfully imported those libraries. Then after that, I have moved on to import our dataset. So this is the dataset that we are going to be using. It's a California house price dataset. So when importing this dataset, I've used the read CSV function from pandas. And inside the brackets, I've passed an argument. The argument is just the file path as well as the file name of our dataset. And then I'm going to be using the head method to display a portion, which is typically the first 5 rows of our data frame. Okay, so I'm going to execute that. So as you can see, this is our data. So by this, we have successfully imported our data. Okay, so I'm going to move to the next step, which will be something to do with the data summary. So I'm going for the data summary. We are going to have a description about our data. So data summary. For this, I'm going to use the info method. So df.info. Okay. So when we execute this cell, you can see we are getting some information about our data. So starting with, we are getting information about the range index, which gives us the total number of entries in each attribute in our data. So you can see we have a total of 20,640 entries. We are also getting information about the columns. So we have a total of 10 columns, which form our attributes. Also, we are getting information about the count. So the null count gives us the count of non-missing value, null count. Okay, so as you can see, we have a total of 20,640 values in each attribute. But for the column total bedroom, you can see that we have a lesser value, meaning that we are missing values in the column total bedroom. Also from the method, we are also getting information about the data types. So basically, the data types of the values in each attribute. So we are having the floating point numbers as well as integers, and for the ocean proximity attribute, we are having objects. The values in the ocean proximity attribute will be text values, or in other words, categorical values. Okay, so by that, I think you have a brief outlook or a description about the data that we are going to be handling. Okay, so moving on, again, we can plot a histogram for the numeric attributes in our data frame, just to have a visual outlook of our data. So for the histogram, so df .hist, so to show that we are plotting a histograms, then I'll say beans equals 50. Then I'll specify the figure size. So fig size 15,9. Okay. Then we will display our chart. So plt.show. So when we execute this cell, this is the output that we are getting. So one piece of information that we can obtain from the histograms, we can see that different attributes have different scale. Okay, so you can see that. Then another thing that we can obtain from the histogram plots is that none of our columns are following a normal distribution. We can see that other columns, most of the columns again, are tail heavy. So the tail is extending further to the right. Okay, so when we will be later on, before we start building our models, we will need to scale possibly to ensure that our data is in a common scale between the different attributes. Okay, so moving on, we can conduct another analysis, which will be the correlation analysis. So correlation analysis. So for the correlation analysis, what we are trying to obtain, or the type of information that we will be obtaining under the correlation analysis. So we are trying to see how the different attributes in our data are correlating with each other. Okay. So for the correlation analysis, I will be using a heat map to represent this information. So correlation matrix. Then the columns that we are going to be using will be the numeric the columns. The correlation analysis will be between the columns with numeric values. Okay, so that includes the longitude, latitude, housing mean value, total rooms, total bedrooms, population, household, median, as well as the median house value. So those are the columns with numeric attributes. Then from here, I'm going to plot the heat map. So for the heat map, I'm going to be using the Seaborn library. So the first thing will be, I'll start by indicating the figure size. So plt.figure. Then state the figure size. So fig size, which I'll say 8x6. Then from here, we use the Seaborn libraries, and we are going to use the Seaborn library to plot the heat map. So sns.heatmap. Then the data will be from this variable, correlation matrix. Then I would like to annotate the figure, so true. For the color map, so for the C map, I'm going to be using Coolworm. Then I would want, so in terms of formatting, I will be using two significant figures, I guess so. So then we format or provide a title for our chart, so correlation heat map. Then we display our plot. So before that, let's say write layout, then plt.show. Okay. So when we execute this, supposed to be fig size. So when we execute this, we are getting our correlation heat map, and from the correlation heat map, you can the values, and from the correlation heat map, you can see we are getting values. These values are representative of the correlation between the different types of attributes. So as when the correlation is closer to 1, then there is a high correlation between the two attributes. So for example, between households and total bedroom, we are having a correlation of 0.98. So this figure is quite close to 1. So between household and total bedroom, they are highly correlated. So by this, you can see that as one variable increases, so does the other. So as the total number of people in the household increases, so does the total number of bedrooms. Also, another highly correlated attributes are between household and the total rooms. I think they're just the same thing as the total number of household of same house. As the total number of household increases, so does the total rooms, which is quite what is expected. Okay, and for our target variable, which is the median house value, we can see it is highly correlated with the median income. So maybe if the higher the house value, the higher the chances of the occupants maybe earning more income. Okay, so for that we can then move on to the next step, which will be about data cleaning. For data cleaning, remember we had a column that was missing values, so we are going to fill those empty values. We are going to fill that. So when filling the missing values in the columns, I'm going to be using the simple imputer. Okay, simple imputer. You can just Google and determine what is simple imputer. So simple imputer, from the scikit-learn, you can see that a simple imputer is a univariate imputer for completing missing values with the simple strategies. So here you can see that you can replace missing values using descriptive statistics, e.g. the mean, median, or the most frequent along each column, or using a constant value. So basically that's what we are going to be using for this case. So I'm going to be using a simple imputer, and my strategy will be the mean. So the first thing while using the simple imputer is to import the library. So from scikit-learn .impute import simple imputer. So that is the model of the library. So then after this, we are going to create a list of the columns, or the column that we are going to impute. So create a list of the columns to impute. And for our case, the column, we only have one column, and that column is total bedrooms. So I'll just copy this, then create a list of the columns to impute. So after creating a list, we are going to create a simple imputer object with a strategy, or in other words, we are going to initialize our simple imputer. So I'll say imputer, say initialize the imputer. So I'll say imputer, then recall the model. So simple imputer. Then inside the brackets, I'm going to pass in an argument, and the argument will be basically the strategy. So my strategy will be the mean. So strategy, I'll say mean. Okay, so it will be calculating the mean in that column, and then fill those missing values with the mean. Okay, then after this, we are going to fit the imputer on the specified columns. So fit the imputer on specified columns. So for this, I'll say imputer dot fit, then specify on the columns. So columns, the column is just the variable contains the list of columns that we are going to impute. Then after we fit, we can then transform. So transform and replace missing values. Okay, so this is this next step. This step, so column, then say imputer dot transform. Then I think after that we can then use again the info method to see if the imputation process was successful. So we can run this from the output. You can see that in the column total, it was total bedrooms. Yeah, total bedrooms. We can see now we have a total null count of 20,640. So basically, with our simple imputer, we were successful with that, and we have filled those missing values with the main value in that attribute. Okay. So the next thing will be about handling the categorical attributes. So the algorithms that we are going to be using, they accept numeric values as input. So they don't accept text input or categorical values as input. So to correct that, we are going to convert the categorical values to numeric values. Okay, and that will be our next step. So we can say handling categorical values. So when handling these categorical values, I'm going to be use the one hot encoder. So to begin with, I'm going to import the library. So from scikit-learn preprocessing import one hot encoder. So we are going to be using a one hot encoder for this case. So again, since we only have one column, which is the ocean proximity, so I'm going to create similar to what I did earlier. We are going to create a list of columns to encode. So let's say we'll create a variable, so categorical columns. So this is, we only have one column, which is the ocean proximity. So I'll just copy this ocean proximity and just paste it in here. Okay. So from this, then I'm going to create a copy of the original data frame. Okay, so that when we are going to apply the encoding process, we don't interfere with other columns in our data frame. So I'll create a new variable encoded df. Okay, then df.copy. So I'm copying my original data frame to a new data frame. So when encoding, we are going to be encoding for the attributes in the encoded data frame. Okay, so that we don't interfere, or if you want to make a comparison or reference, we still have our original data frame. Then after this, I'm going to create an instance of one hot encoder. So create an instance of one hot encoder. So this is our next step. So for this, as I'm going to say encoder one hot encoder. Okay, so we are creating an instance, and inside the brackets I'm going to pass several arguments, and one of the arguments is sparse output. So sparse output, basically with the sparse output is that I don't want to generate a sparse array. I want to generate a dense array. Okay. So that's why I'm specifying this. So for sparse output, I'm going to use a Boolean false. Then to drop the first instance of the category of each variable, I'm going to drop equals to specify first. So then from here, we are going to start performing the one hot encoding, and I'll be using a for loop. So we'll be iterating through each categorical column. So for column in categorical column, from here, we are going to fit and transform the selected columns. So fit and transform. So I'm using this comment so that they can easily guide you what I am doing. So I'm create a new variable. This variable is the one hot encoded. We'll call it one hot encoded. So for this variable, as I said, we are going to fit, and we are going to use the instance that we created earlier. So Control C, I'll just copy paste this here. So encoder.fit transform. So we are transforming the encoded df column. So after we have fitted, we are going to create a data frame with the one hot encoded columns. So basically we are fitting and transforming the categorical columns. Then after that, we are going to create, since it will generate different columns, we are going to create a data frame with the one hot encoded columns. Okay. So for this, we can say, we can use a comment and say, create a data frame with one hot encoded columns. So I'll say, I'll create a new variable, one hot df. Then PD, when creating a data frame, we use the data frame function. So data frame. Then the columns that we are going to specify the variables. So that is the one hot encoded. And then inside here, I'm going to use another argument, which is that will enable me to rename those new columns that we have generated. So columns, and this I will be using the encoder.get feature names out. So I'm going to use that method. Then column. Okay. Then after this, we can then concatenate the one hot encoded data frame. So concatenate the new. No, it's supposed to. We are going to concatenate this one, the one hot encoded data frame, the data frame that we have created above. So we are going to concatenate. We're going to concatenate the data frame. Okay, so merging those columns that we created together. Okay, so encoded df. Let's say pd.concat. So we'll say encoded df and one hot df, and this we are going to do this along the axis. Axis equals 1. Okay. Then after we are done with that, we are going to drop the original categorical column. Okay, so drop the original categorical column. So we are going to drop that. So encoded df. So I will say encoded df dot drop. We are going to drop that column. So we just pass in the list, the variable that contains the list of the columns that we're just going to pass in the variable that contains the list of the columns that we are going to drop. Okay, so categorical columns. So by this again, along the axis x, so axis equals 1. We can also, since we were using the for loop, you can also use the column here inside this bracket. Okay, so it depends with what you prefer. Then after this, we can then display. So I will say I will recall the encoded df. So encoded df dot head. Okay, so when I execute this cell, oops, we are getting an error. Encoder, one hot encoder, supposed to be, okay, spelling mistake. So it's supposed to be sparse with an S. Okay, so when I run that, oops, we're not getting another error. So we need to, we'll use this column because we were iterating using the for loop. So when we run that, you can see that we have now encoded our the ocean proximity column, and we have, as you can see, we are added 4 columns. Okay, that's the ocean proximity inland, ocean proximity island, ocean proximity nearby, ocean proximity ocean. So with the one hot encoding, we are producing a matrix. Okay, and for this matrix, so with the one hot encoding, so basically this is a technique used to convert the categorical variables into the binary matrix. As you can see, that's what we have done, where each unique category becomes a separate column. As you can see, we have created separate columns with binary values, so either zeros and ones, indicating the presence or absence of that category. Okay, so that's basically that's what we have achieved using the one hot encoding. Okay, so we have encoded the column that contained categorical values. So the next step after this will be all about now starting the modeling process. Okay, so we are going to start now to see how we can apply those algorithms. So to begin with, we are going to define the features as well as the target variable. Okay, so define the features and target variable. For the dependent variables, I'll label those as x. So df. So because our median house value is our target variable, okay, so what I will do for our dependent features, I'm going to drop each and every other column except it will be each and every other column except the median house value. So the quickest way to do that is to just drop the median house value. Okay, so I'll use the drop function. So df dot drop. Then so we are going to drop the columns. Then I will just specify the columns that you're going to drop, and the column will be the median house value. Okay, so just use this. Okay, and for our target variable, it will be the median house value. So I will just use that in here. Okay, so when I execute this, oops, we're getting an error. So it's supposed to be columns, so just a small mistake. So, okay, so that's it. So we have defined our features. So when we say the X, it will be our independent, the dependent variables, our features. Then our Y will be our target variable, okay? So from here, we then move on to the next step, which will be about splitting into training and testing set. Okay, so basically this is splitting data into training and testing set. I'm going to import the library that we are going to be used for this, and that will be the train test split. So from sklearn dot model selection import train test split, train test split. Okay, so we can run that. So we have imported that model. Then we are going to conduct the splitting. So for the splitting part, I'm going to use the common, what we oftenly use. So the X train, so X train, X test, Y train, Y test. So for this, again, we are going to recall our the model that we are going to be using for train test split. Again, so I'll just paste it there. Then X, which represents our dependent variables. Then Y, which is our target variable. Then the test size. I will use 0.25 or say 0.25. Then I'll specify the random set. So random state, which is the set value. I'll say 42. Okay. So I'll execute this. We have successfully separated our training and testing data. So the X train and the Y train will be used for training, while the X test and the Y test will be used for testing and evaluating our model respectively. Okay. So after doing that, we are going to go to the feature scaling. So earlier on, we saw that different attributes are having different or are in different scale. So for feature scaling, if you have numerical features with a different scale, for example, our case, it's appropriate to apply the standardization, or also known as the Z-score scaling, to ensure that the features are of the same scale. So in standardization, which is also known as the Z-score normalization, we are going to transform the features so that they have a mean of 0 and a standard deviation of 1. So that's what we are trying to achieve here. And this is achieved by subtracting the mean from each data point and dividing by the standard deviation. And it makes our data follow a standard normal distribution with a mean of 0 and the standard deviation of 1. So, and you might ask yourself, why are we doing the feature scaling? So without scaling, features with large magnitude may dominate the learning process. So basically, we are trying to avoid that. So this can lead to model being biased towards those features, and it will be ignoring the other features. So to avoid that, that's why we are doing the scaling. So the scaling ensures that all features are treated equally in terms of their contribution to the model's prediction. So basically, that is what we are trying to achieve with this. We are trying to reduce the biasness of the models so that each feature or each attribute has are treated equally in terms of their contribution when we are doing the predictions. Okay. So for the feature scaler, I'm going to start by importing the standard scaler. So again, from sklearn dot preprocessing, import standard scaler. Okay. Then we are going to initialize the standard scaler. Again, initialize initialize the standard scalar. So for the initialization, we are going to say scalar. So scalar equal standard scalar. Okay. Then after we have initialized the standard scalar, we are going to fit the scalar. We are going to fit and transform the scalar on the training data. So fit and transform the training data. So here we are going to say x train scaled. So we are going to recall our scalar. So scalar dot fit transform. Okay, so we are transforming our x train data. Okay, so after we have transformed our data, we are going to use the same scalar, but in this case we are going to transform now our testing data. So transform the testing data. So here it's supposed to be transform. So for the testing data, again we say x train, supposed to x test scaled. Here it will be scalar dot transform. We are transforming our x test. Okay. So when I execute this cell, oops, we're getting some error. So x train scalar is supposed to be fit transform x train, saying that will not convert string to float. We have a problem. Oh, okay, there's something that we forgot to do that is making this error. So we were using the encoded df, not df. Okay, so remember earlier on we created a copy of the original data frame where we, moving forward, we used the encoded df, but I want to now from encoded df, I'm going to copy that again to be used so that we can use df. So basically what you can do, just after this, we can say, we can create a new cell here, and in this cell, you can say encoded. So df, you can say encoded df dot copy. So we are copying the data frame that we, after the one hot encoding, so we are copying back to what we originally called our data frame. Okay, so df. So I'm going to, when this, so we can say df dot head. So when we execute this, you can see now we are moving forward. We'll be using the df. Okay, so after this, we can run this, then this, then splitting, then we can run every other cell until okay. Now we see the errors. Now we have now sorted that error. So to see if you are successful, we can see how the transformation has occurred. Okay, by running this. So when we x train scale, you can see we have transformed our data. Also for the x test scale, you can see again we have transformed our data. Okay. So after transforming our models, and then move on to now building the models. Okay. So for the models, I'm going to start with the linear models. So I'll start by importing the libraries. So from scikit-learn linear model, import the linear regression, lasso, ridge, as well as the elastic net. Again, I will also import the evaluation metrics or the modules that we are going to be using under this. Those include the mean absolute error, mean squared error, and the R-squared score. Okay, so for the modeling, I'm going to start with the linear regression. So I'm going to build a linear regression model. So for the linear regression, I'll start by creating an instance of the linear regression. So linear model, so I've just shortened that. So lin model, then the linear regression. Okay, then we are going to fit the model to the training data. So lin model dot fit x train scale and the y train. So we are fitting that on the training data so that our model can learn the relationship between the independent as well as the dependent attributes in our training data. So after our model has learned that that relationship, we are now going to use that to predict now using our testing data. Okay, so when I execute this, okay, I did not run this cell, so let me run this cell to import our modules. Then I'm going to run this cell again. As you can see, now we have performed the linear regression, starting by fitting our model to the training data, then making predictions. Now we are going to now use the evaluation metrics to determine how our model is performing. So we are going to evaluate the model. So for the mean absolute error, so the mean absolute error, the function, and inside the function we are passing in the y-test. So y-test is the actual values, while the y-pred-lin, these are the predicted values from our model. Okay, again for the mean squared error we are doing the same. Root mean squared, as we said, is the square root of the mean squared error, and the R2 score, so we are using the R2 score function. Then we are we are determining the R score between the y-test and the y-pred and the predicted values. So when we execute this cell, the information that we're going to get is the different evaluation metrics from our module. So for the mean absolute error, we can see our model is making an average mean absolute error of 50,329.95. The mean squared error, you can see it's a huge figure. Root mean squared, as you can see, it's also large, while the R2 score is 0.63. Okay, so that was for the linear regression model. So we can repeat the same for the lasso regression. Everything will be similar to what we did earlier. So for the lasso model, I've created an instance of the lasso regression, and inside the bracket I've used the maximum iteration. This is 5 million. Then after we have created our instance of the lasso regression model, we then fit that onto our training and onto our training data, then so that our model can learn the patterns or the relationship. Then after that, we make predictions using that model, using our testing data. Then from there we move on to how we are going to evaluate our model. This is how we evaluate our model. So I'm going to execute this cell. Boom. Then this is the output that you are getting from that. So basically, I think you have seen how we are creating an instance of the model up to evaluating the model. So and by now I think you have seen that this stuff is just repetitive. Okay, so to make our work easier, again I'm going to be using a for loop. So the for loop will make our work easier and make our code shorter. So let me use that. So the first thing that we are going to be doing is importing the necessary modules. So if you're going to use the for loop, this is what we are going to be doing. So you start by importing the libraries of the algorithms that you will be using. So these are the linear, lasso, ridge, as well as the elastic net regression. So for the other two algorithms, the KN neighbors as well as the SVR. So these are the modules for that. So these are the algorithms that we are going to be comparing in this analysis. Also, you can also import the evaluation modules. So this we had already imported this, but if you decide to start from here, this is how we will go about it. So we import those modules. Then we are going to define the models. Here we are going to create an instance of each using a dictionary. So models equals to, then we create a dictionary. So here we'll say linear regression. So linear regression, we create that model for that. So linear regression, linear regression. So we create an instance for that. Then we move to the other one, which is the lasso regression. So lasso regression. Again, we create an instance for that. So lasso. So don't forget, otherwise it will bring us an error. So last time I used 5 million. So 5, that is 5,000. Okay. The next will be ridge regression. So again, we create an instance for that, ridge. So you can do the same for the other models. So that's the elastic net and the KNN regression, as well as the SVR. So after creating the instance of the models that you're going to use, then I'm going to move on and initialize or create a dictionary, which will be storing the results of after we have conducted the evaluation. Again, here I will be using a dictionary. So I've initialized a dictionary to store our results. So I've created a variable with the name results, so the brackets. So I've specified the model, mean absolute error, mean squared error, root mean squared error, and the R squared score. Then from that, we create a loop to iterate over the models. Okay, so for model name, model in models dot items. Okay, here we are going to start by fit the model to training data. So model dot fit. So x train scaled, then y train. So after this, so we have fitted. Then the next one will be making predictions. Make predictions. So for when predicting, we'll say y pred. We'll recall the model. So model dot fit. No, here we are predicting, not fitting. So predict. So model dot predict. Then x test scaled. Okay. So after we made the prediction, we then moved on to evaluating the model. Okay, so we move again to evaluating the model. Remember, we are still in the for loop. Okay, so the for loop will just solve each and every problem that we are giving it. Okay, so by this we are not going to making writing more lines and more lines of code. So in terms of evaluating the model, you can just copy this. So we can just copy that and then beneath here we paste it, and make sure it is aligned. It is so that it's inside the loop. So we just correct this. After making the predictions, we then move on to the next, which will be about, remember we created this dictionary up here. So the data that it will be in that dictionary, so we are going to that. So then after we have evaluated our model, we are going to store the results in a dictionary. Store results in a dictionary. So for this, we say results so model, so the models for each. So I'll use the append function. So append model name. So the model will contain the model name. So the model name as the column name, it will be containing the model names in our data frame. So and then results here, it will be the mean absolute error. Again, dot append. Append. So here it will be MAE. Again, results. This one will be MSE. Then you can just say append. Again, MSE. So you can repeat the same for RMSE and R squared score. Okay, so this is for it. Then after this, since we have creating these different columns, we can then create a data frame to merge these columns. So results, I call it that as results.df. So results df. So since we are creating a new data frame, we call the pd.data frame. Then results. Okay. So here we can create another comment and say create a data frame for the results in dictionary, or results in dictionary. Okay. Then after this, we can then display, which is results dot results df dot head. So when we execute this, we are getting an error. Module pandas has no attribute data frame, so it's supposed to be data frame. Okay, so this is the output. We have how many? 1, 2, 3, 4, 5, 6. So we can just insert here 6 so that we display each and every algorithm and their evaluation metric. So this is the output. As you can see, we have generated a new data frame containing the columns model, mean absolute error, mean squared error, RMSE, and the R squared score. From the look of things, you can see that for the mean absolute error, you can see that the linear regression, lasso, and ridge regression, all of them are almost having the same values. And elastic net, which you saw, is a combination of the 3 modules, regression models. You can see it's we are getting a slightly higher values than the 3. So it has a mean absolute error of 56,525, and the R squared from that is 0.5652. For the KNN, this is the model with the list. Okay. So KNN has the list mean absolute error. So for this case, you can say that KNN regression is the best model that we can use for further when building our model. because we are getting the least value of the mean absolute error, mean squared error, the root mean squared error, and we are getting the highest value in terms of the R squared value. For the support vector regressor, it is the least accurate model. For this case, we are getting a higher mean absolute error. And when you look at the R squared score, is a negative 0.04. So basically, it's just telling us that I'm not the correct model for this type of data. So for the interpretation of the evaluation metrics, like the ones we have discussed earlier, oftenly they depend on the nature of your target variable. So basically, you can see that we are getting large values in terms of the evaluation metrics. So you might we might think that our model is not correctly working. So for the R squared, this represents the proportion of the variance in the dependent variable that is predictable from the independent variables. So it ranges from 0 to 1, and 1 indicates a perfect fit. So for the K and N regression, we are getting the highest 0.71, which is which is much closer to 1. So it indicates a better fit than the other regression models. So the R squared is a measure that tells you how well the predictions of the model match the actual data. Okay, so when you convert this to a percentage, you can say at 71%. Okay, so basically the R regression indicates the goodness of fit of our model, and from this we can say the K and N regression performs way better than the other models. Okay, so the huge MAE, MSE, RMSE values, so these metrics are influenced by the scale of our target variable. Remember, we did not scale our target variable in this analysis. Okay, so our predictions will be more dependent on the target variable. So if the target variable has large range of values, as we saw, the absolute and the square difference will obviously be also large. Okay, so this does not necessarily mean that the model is performing poorly, especially if the predictions are still capturing the underlying patterns. Okay, so you can look at the R squared information as well as the mean the other metrics. So obviously for the mean squared error, mean absolute error, and the RMSE, obviously if you have a lower value, it indicates the goodness of your model. Okay, so I think that's about that. Also, we can using Plotly library, we can plot a bar graph to represent this information from our table. So I'm creating a bar graph using Plotly. So our results from the results DF, then our x-axis values will be the evaluation metrics, while the y will be our model. Then I've supplied the title, evaluation metrics. Then I'm created for the bar graphs. I will be grouping those bar graphs together. Then I'll move on to customize the layout. Okay, then set the figure size, then display our plot. So when I run this is the output that we are getting from that. As you can see from this chart, the key, you can see we have the variable. So let me remove this. So you can see how the different algorithms are performing according to the mean absolute error. So SVR has the largest mean absolute error, making it the least likely model that we can use for this analysis. For the KNN, this one has the least mean absolute error of 40.9671. Okay. Elastic net regression has the second largest mean absolute error, so making it again the least desirable algorithm for this case. Okay. When you compare the R2 score, the R2 values, again, this is how you can visualize that information using bar graphs, you can see how the different algorithms are performing. Okay, so that's how you can do that. Okay, so we represented this information using a table, and we have also using bar charts to represent our information. So with this, it's very easier, and you can see that if you are going to select the model based on the R-squared score, then again you can see that KNN regression is performing way better than the other regression algorithms. Okay. One last thing that we can do before we call it a day is we can plot a scatter plot to represent, to see how the different models were, how we can use a scatter plot to represent, how to see, to visualize and see how the different models are performing. So for the scatter plots, the first thing that we will be doing is we are defining the grid layout. So for the rows and columns, so we are specifying I want 3 rows. Okay, so I have 6 models. So for the models, I want 3 rows, meaning I want 2 models per row. Then I want 2 columns. So okay, then we are going to specify the figure size of the entire grid. So plt.figure figure size 10,8. Then again, you are just going to be looping over the models. So for index model name in enumerate, so we are using the enumerate function. Then after creating our loop, we feed the models the training data. Then after that, we make predictions just as we did earlier. Since we are creating a scatter plot, so we create that. So for the scatter plot, then we define the subplots, rows, column, and the index. Then we use the matplotlib library to plot the scatter plots. For the scatter plots, it will be the y-test against the y-pred. Then we are using an alpha of 0.5. So that will be the transparency of the points on our chart. Then we want to include the line. So we want to also include a diagonal line to the plot, which represents the scenario where the predicted values are equal to the actual values. So we want to have that line in our scatter plot, and the line style will be dashed. The color will be red with a line width of 2. Then we set the title of our scatter plot, then the X label and the Y label. Then we plot our chart. Okay. So when we execute this cell, again, it will take some time. So these are the scatter plots. And also, just by looking at the scatter plot, you can see, you can determine the accuracy of the model. So you can see for the SVR, we are not getting a good fit. So basically, we saw that. For the KNN regression, you can see how the model is fitting. So you can quite see a good balance in terms of the points above and below the diagonal line. For the linear regression, lasso, and as well as the ridge, you can see quite a similar pattern. So for the scatter plots, with reference to the KNN regressor, the scatter plot for that shows a strong positive correlation between the actual values and the predicted values. So with its accuracy, while not quite perfect, the k-nearest neighbor model demonstrate a good ability to capture the patterns in the data and make predictions that quite align well with the actual outcomes. So that's how you can plot a scatter plot and obtain and visually represent your data. So overall, in summary, we can summarize what we have discussed earlier. So for the mean absolute error and the root mean squared error, lower values are what we are what we look at when we are going to rank the model. So when we are going to rank your model to see which model performs better, we will prefer a model which has the least mean absolute error as well as the root mean squared error. For the R squared value, a higher value that is closer to 1, a model with a higher value of R squared that is closer to 1 indicates a model is better fit of the model to the data, as we have seen with the KNN. Okay, so when evaluating a model, it's often advisable also to consider the multiple metrics as we have done. So we have seen how the models are performing within the various evaluation metrics, so that we are able to get a comprehensive understanding of the performance, especially since each metric provides its unique type of perspective. Okay, so I think that's all for today. Thank you for your time. And before we sign off, again, please consider subscribing to our YouTube channel. We are welcoming you to our wonderful community. Hit that notification bell so that you never miss any of our video updates. Okay, so until next time,